Leetcode 295, find median from data stream. It's a hard problem, but it's definitely not the hardest of the hards. And all I'm trying to say is don't get discouraged. So some people, whenever they see hard, they think that it's definitely out of their league. But at least in this particular case, if you are able to tackle mediums on your own, I think you should be really good to go and try to solve it on your own. So here is the description. The median is the middle value in an ordered integer list. And so in basic statistics, you have couple different ways to measure central tendency, like an arithmetic average, median, mode, range, and so on. And here we will be talking about medians. And a lot of time people say that medians are better than averages because, for example, averages can be really influenced by outliers. So let's say if you have 3 people, you have a group of 3 people, and 2 of them are, let's say, earning 30K per year, and the last one is a multi-billionaire. Then if you take average of their income, then all of them are billionaires. Yeah, but if you take the median, then the one that's in the middle would be representative for the group. That's why a lot of people prefer median for certain descriptions and not averages. And here is the rest of the description. If the size of the list is even, there is no middle value, and the median is the mean of 2 middle values here. So basically median has, there are 2 different formulas to calculate it, depending on the number of items or the number of elements inside your list. And here is an example. If you have an odd number of elements, then you just take the one in the middle, exactly. But if you have an even number of elements, then you cannot take the one in the middle, since there are 2 elements in the middle. And what do? You take both of them, you sum, and you divide by 2, so you take the average of those 2. And our task is to implement methods of this class, median finder. And we have a constructor or function for initialization of median finder object. Have to put something here. Then we have to take care of 2 methods. One is called addNum. So basically we'll have a stream and we'll be adding data one by one using this method. So as we as someone would call this method, we have to keep track of everything that was added to the stream till now. And at any point they can also call find median. And we should return the median of everything that was collected till this point in the best or the most optimal way. So here they added some description. So addNum adds the integer num from the data stream to the data structure. So we have to keep the history of elements that have been added, and the median returns the median of all elements so far. Answers within 10 to the minus 5 of the actual answer will be accepted. So of course, with those divisions, you cannot always get an integer. Sometimes you'll get float, so that's why they will have to check within a certain accuracy. So we can simply use in Python normal division, and it should be okay. And here is an example, just single example. If the input is not the actual input, just a description of what will happen. First, they are creating the median finder object, and they will initialize object of this class, and then they will call addNum and addNum with following arguments. First they will add 1, then 2, and then they will try to calculate median. And of course we have 2 numbers, then 1 plus 2 is 3, 3 divided by 2 is 1.5, and that should be returned whenever the find median is called on that array that we have collected so far, and then addNum again. And as you can see, we still have memory of everything that has been collected. So this 1 and 2 is still there, and then we add 3, and this is just an example that here they are adding them in such a way that each number is greater than the previous one, but it doesn't need to be the case. Yeah, so they can be added in any order with any number of repetitions and so on. And in this case, of course, we have an odd number of elements, so we can return simply the element in the middle. Okay, so let's try to figure out what would be the best way to tackle this problem. So the first two hints are inside the title. We want to find median from data stream. Yeah. And both median and stream point to a particular data structure called heap. A heap, which allows us to retrieve either the largest or the smallest, depending whether we have max heap or min heap implemented, element in O1 time complexity. Yeah, so we can retrieve either the smallest or the largest element very fast. And whenever we have median, then we would want to have the data separated into two groups. Yeah, the smaller part and the larger part, and we will take the largest element from the smaller half and the smallest element from the upper half, and return the average of those two. Yeah, so inside to calculate the median, we will use both heaps at the same time, but there are of course many other problems which can be solved using heaps, like for example kth largest element or its smallest, or something like median, of course, minimum, maximum from stream / real-time data / online, all of those words, or maybe even merging sorted collections like arrays or lists. Yeah, and whenever those keywords appear in Leetcode style problem, then probably we can use a heap. And I say probably, not for sure, since there is nothing sure. Those are just hints that you have to use, but you still have to understand why is it the case. And I'm just trying to say that the chances are, if you see those kind of keywords, that you may use heap for optimal solution. Yeah, so those are the keywords that you can use whenever you find them inside Leetcode style problem description or title. Yeah, and what is a heap? So let's first discuss heaps, maybe not in great detail, but just generally, and then we will try to use them to calculate the median. Yeah. Usually heap is a binary tree such that, and here we have two options. In max heap, we will have each element being is larger than both of its children. Yeah, and min heap is exactly the opposite. And binary tree, of course, you have at most two children for each node. That what binary means. And min heap, each element is smaller than both of its children. Yeah, and that means that for the max heap, the largest element is where? At the root, the very first element. And for the min heap, the smallest element is in the root. That means that we know exactly where it is and we can retrieve it in a very fast way. Yeah, so getting largest, smallest element is very fast at O1 time complexity. And another thing is that insertion is relatively fast. and generally is done in log n, yeah, time complexity, meaning that is faster than linear insertion. And there are some relationships between indices as well. So for element with index I, what do we have? The parent is on the following index. Parent is I over 2. Floor, so I will not be able to draw it, but generally you want, of course, the integer division. So we can also use Python notation, I hope, for that. And left child is on index 2i, and right child is on index 2i plus 1. Yeah, and where are those indices? Those will be indices of an array, which will store the elements of heap. So usually heap is implemented using an array. Yeah. So an array is used to store the nodes. Not this one, that one, not the diamond, but okay. So those are important information that we already have. And the next thing is how to move from this to finding median. We already said that we will use both max heap and min heap. And one important thing for Python is that only min heap is implemented in Python or inside the standard package. Yep. So this one has Python implementation, but the other one doesn't. So what we can do, we can implement max heap on our own using the min heap. So basically the trick is, since here, I think all the elements, no, they don't have to be positive, even though in the examples they were positive. But either way, we can simply invert the elements for the min heap, meaning we can multiply them by -1 and store them in a min heap after multiplying by -1. And in this way, the min heap will work as a reversed max heap. Yeah? And we can simulate min heap using max heap using min heap. Yeah? So we will have to implement using min heap. Let me also switch to like this. Okay. So now let's write down high-level overview of how to get the median. So how to store and retrieve median efficiently. And we need to implement those two functions. So let's copy it from here. What will happen here and what will happen here. So the first thing is to use two heaps, min heap and max heap, to store upper and bottom half of the data separately. Yeah, and that is the most important part. So here, what will happen here and what will happen here? Let's start from add num. First thing, we will always add the number to the lower half, and that will be our max heap. And it will take care internally of sorting. Yeah? So we can always insert and we can always retrieve the maximum in efficient way, no matter what was this number, whether this number was the biggest or somewhere in the middle or maybe the smallest so far. We simply add it to the max heap, to our lower half, and it will take care of the sorting on its own. Yeah? And then get the current max out of the lower half. Yeah? So we don't know if this one was the max or in the middle or the smallest. It doesn't interest us. We simply add it to the lower half. It will take care of the sorting, and then we get the maximum that is currently there in the lower half. And insert or add to the upper half, our min heap. And not the number, but the current max from the lower half. At the current. So here we are retrieving it, then we are adding it, and then we need to keep the halves balance. Yeah, so we need to have exactly the same number of elements in the lower half and in the upper half, or the lower half can have one excessive element, yeah, at most. So now we check this condition. If length of upper half is greater than lower half, then pop the smallest element from the upper half and add it to the lower. And that's it. So 5 steps, high-level steps in total. And inside find median, it's already easier. We have two options. Either upper half and lower half, and sorry, here also length. Yeah, either they have the same number of elements, or the lower half has one element more. If so, if they have the same number of elements, then what do? We use median for formula for even number of elements, and this will be the max from the lower half plus max from min from upper half. Let's just take this out, and of course divided by 2. And otherwise, else we will simply return the max from lower half. That's it. That's the whole solution. Well, now we have to translate it to Python. And first things first, we need to create our max heap wrapper. So inside init will store some array. Yeah, this will be our internal data. And then we need to have push functionality where we push a number. And we need pop functionality. And we need length. Which will be simply the length of this. And we need the top, which will be what? Self data on position 0. Yeah, and here we could check if the length is greater than 0, but let's not complicate it initially. If they don't check it at any point inside the test cases, then we don't need to worry about this. And because theoretically one can call top when the data is empty, but because this is just like a helper for us, we don't need to make it perfect. Only as much stuff as needed. And we will here use the heap queue functionality to heap push and self data and number multiplied by -1. Yeah, and in this way, since the number will be multiplied by -1, we can use this heap queue, which is min heap, as max heap. Yeah, and otherwise return heap queue heap pop from self data. Yeah, so now we need two halves. The lower half will be this. And the upper half will be a list. And now we have to implement what's happening here. Yeah, so first we add the number to the lower half. So we call our push, yeah, and add the number there. Then we get the smallest value. And the next thing is the smallest value from the lower half, and we add it to the upper half. Yeah, so serve low pop and self up heap push value. And now we need to check if the length of the upper half is greater than the length of lower half. So self up is greater than the lower half. If so, then what should we do? Pop the smallest element from the upper half. Yeah. So let's go this. And instead of heap push, we do heap pop. And we add it to the lower. Yeah, and now we have two options. Either they have the same length, in which case in total we have even number of elements. Our max row would be and here top and min up will be self up on the first index, and we have to return the average between both of them. Otherwise, we just take the biggest element from the lower half. Okay, let's see if I made any mistakes. If I made any mistakes. Okay, wrong answer. Okay. Looks good. Yeah, here. As I have forgotten. Indeed, I made a mistake here. So let's see. Since we have inverted it here, but I forgot it to invert in those two places. And looks good for the initial test case. So let's see if everything works fine for all the other cases. And we beat around 20%. And usually when it's the case, if you rerun it a couple times, you can get a little bit better results, since there are very little test cases. Yeah. And it really depends on how the servers are overloaded and so on. Yeah, so in this case, we are around 20%, which is not that bad, but not that good as well. But I think if we rerun the same solution, we can get up to here. Yeah, but probably for the best optimal, you still have to add some more optimizations.